Hello, friends. Here's a quick overview of what we sort of did in class on Wednesday. That will help you for the homework. The first example involves some carts that are each of mass 500 grams. Remember, 500 grams is actually 0.5 kilograms, which is what we're going to want to use in the equations. And each of these carts is attached to each other via a string. Now, the whole concept of tension is that in a string, the tension pulls away from an object. But if you notice, if two objects are holding a rope, which is always the case, then the tension pulls inward or away from both of them. So it's actually pulling back on this cart to the left and to the right on this cart. Let's choose positive to be to the right. And we'll call the tension in this rope F3, the tension in this one F2, and the tension in the rope that's pulling it via hand, we'll call that F1. That means this is negative F3 because it's pulling to the left, which is negative. Remember, negative just means a direction, in this case, left. And this one will be positive F3. So the tension in a rope, is the same in both sides of a rope. Meaning one side of a rope doesn't pull more than the other side. So if it's 10 newtons pulling on you, it's 10 newtons pulling on the other person. And that should make sense because of, I hope this makes sense. If these weren't equal, then the rope would move because the net force in the reference frame of the rope must be 0. Otherwise, the rope wouldn't stay as it is. Meaning if you were pulling more on one side, it would stretch or it would compress, but the rope stays as it is. So it's the same on both sides. Except that one is negative because it's left. So the same with F2. And the same with F1. Notice that the positive is for any rightward force and the negative is for any left force. In all of these, we also have normal force from the surface pushing up and gravity pushing down, and those will just equal for all of these. In the vertical, that's easy. These aren't jumping upward, right? They're not landing or bouncing. There's no incline. They just cancel. So the horizontal is all that matters. So we'll call this cart 1, cart 2, and cart 3. For cart 1, cart 1 is experiencing a force to the right, F1, and experiencing a force to the left, F2. Now, which one's bigger depends on what's going on. Let's say that they're accelerating to the right at 4 meters per second, which is positive because it's to the right. Emphasize that's positive. So if A is to the right, then Fnet is also to the right, and then F1 is greater than F2 in magnitude. which means Fnet from the diagram is F1 minus F2. I mean, that doesn't need to be the case. This is always F1 minus F2. Fnet will always be F1 minus F2, no matter what the acceleration is. Remember, this is independent of the acceleration of motion, no matter what. This is true. We haven't set it equal to MA yet. So remember that. That's so important, right? Fnet comes from your diagram. Then you set it equal to MA, right? So that means F1 minus F2 equals mass times acceleration. Then you do that. And that's that. So notice we have M, cool. I have A, but I actually don't have F1 or F2. How do I figure those out? Let's go to cart 3. So cart 3 will help us do that. So cart 3, the only force acting on it is F3, if you remember from the previous one. It's just F3. We've canceled the vertical, so I'm just looking at the horizontal. So Fnet is F3. There's no minus. There's no other force. It's just that's it. Equals MA. M is 0.5 kilograms. A is 4 meters per second per second. Those were given, or those that was from, like I just gave it that mass and I was giving it that acceleration. So 0.5 times 4 is 2 newtons to the right. So the net force is 2 newtons to the right. It equals F3. So F3 is 2 newtons to the right. Great. If I look at cart 2, cart 2 is the same as cart 1, where we have that same tension that was pulling the cart 3 is pulling back on cart 2. They're pulling on each other. So actually F3 is acting to slow cart 2 down, which means F2 has to pull extra. The way to think about that is this, I think, should be so intuitive. If this string weren't there and these two were just attached by, glue, then F2 would have to pull more because it's pulling more mass. But this is represented in the fact that for cart 2, F2 is positive, F3 is negative. So F2 is bigger than F3 if it's accelerating at 4 meters per second to the right. That means Fnet is to the right, which means F2 magnitude-wise is greater than F3. And F3 was 2 newtons. But we'll do it in a second. No matter what, Fnet equals F2 minus F3. No matter what. Forget this number. Block it out. This is always the case. And then that equals MA separately. So F2 minus 2 newtons equals M, 0.5, times A. So notice this is cart 2. This is only 0.5 kilograms. I'm not including cart 3 in the mass here. I know I said separately if they were attached by glue and there was no F3, separately, so this is separate analysis. It's doing weird things. Separate analysis, I have 0.5 kilograms attached to 0.5 kilograms. It's essentially 1 kilogram, and F2 is just pulling it. Say there was no rope between the last two carts. Then F2 would be the net force. There would be no F3 fighting back, and it would just be more mass. So F2 would be 4 newtons. Notice that's the same as if we do it this way. So here we have 0.5 is the mass of only cart 2. I hope this was okay. I hope this makes sense. If it didn't, just erase it. Forget about it. Right? What you want to do is focus on one object at a time. Let that sink in. One object at a time. Cart 2 is our object. Don't include cart 3. I know I did right here. That's because if they were attached, I'm just showing it gives you the same answer. Right? Cart 2 is 0.5 kilograms. The forces acting on are F2 to the right, F3 to the left. This is F net equals M of cart 2 only times A, which is 4, which is 2 newtons. So F2, and I add 2, 2 plus 2 equals 4 newtons. Same answer. Positive 4 which means to the right. So positive means to the right. Which obviously it was. That's why we drew it. We knew it was positive. If we got it was negative, then something went wrong. Or it means it was somehow was pulling to the left, which might be possible. But the point is we got 4 newtons, which is the same as if they were attached. And that should make sense because this string doesn't know about this string. It just knows that it's pulling 1 kilogram, regardless of how these are attached. But if you draw a force diagram on cart 2 alone, it confirms that that indeed is the case, that it's being pulled back with 2, to the right with 4, so its net force is 2 newtons. So F net equals 2 newtons. F net equals F2 minus F3. So this is 2, right? So F2 minus 2 equals 2, so F2 equals 4. Cool. Don't overthink it. Just those steps one at a time. So back to cart 1. Cart 1 had negative F2, positive F1. Mass of 0.5 kilograms. Right, F net equals MA. F2 was what, 4 newtons? In this case, it's to the left, so it'll be negative. F net equals F1 minus F2. Separately, F net equals MA, 0.5 times 4. So for all of these carts, the net force on them was 2 newtons. They're all moving together at the same acceleration. They all have the same mass. So all of them experiences 2 newtons to the right total, which means that this equals 2. So F1 minus F2 is 2. F1 minus 4 newtons is 2 because we solved for the last one. The tension in this one is 4 newtons. So F1 is 6 newtons to the right. That's it, right? You can pause that if you need to go back. So if I have some masses dangling from each other and each has mass M, draw a force diagram on this mass. What does this mass experience? Well, this mass experiences, call this F1, F2, F3, F4. It experiences, let's say positive is, we can make positive down, I'll make positive up. Positive F4 up, negative F3 down. It's not moving, right? The acceleration is 0, the velocity is 0, they're just hanging there. Now, if they were moving, it'd be a little different, but I'll just have them hang for this one. Then F4 equals F3 because the F net is 0. F net is F4 minus F3, which is MA, which is 0. So F4 equals F3, which you just know those cancel. So in this diagram down here, we have FG. Oh, sorry. I forgot something very important. Did you see that? Wait a minute, where's gravity in this? That was funny. In the card example, I got used to that. Gravity was up and down, where there's no gravity in this one. Here, there's gravity. Did you guys, I don't know if any of you caught that. I'm happy I did. I'm happy I caught that. So what do I need? Gravity to be positive or negative? It's down, so it's negative. You see my thought process? I'm thinking out loud. This is what you want to do. I draw it. I know it's down. I made positive up, so it's negative. Great. So minus FG equals 0. which means F4 upward, the tension in this rope is the tension in the bottom rope plus mg, because remember Fg equals mg, which means which is bigger? F4 by mg. So mg bigger. So here F1 equals mg. Here F2 equals 2 mg. Here F3 equals 3 mg, because lifting all three. And here F4 equals 4 mg, which indeed is, notice it's bigger than F3. So the tension in this is one of the weight of this mg, that value bigger than this one. And then this one's mg bigger than this one, and this one's mg bigger than this one. The point is, look what I did. Up minus down, even if there's two going down. I totally forgot gravity. We're not floating in space. We're on the Earth, so there's gravity. Gravity points down, so we include it. Notice that in the card example, we didn't include it because it canceled the normal force. So the verticals canceled, F net vertical is 0. We just look at the horizontal. We're here, it mattered. We're here, the tension is bigger than mg, or mg bigger than the tension below it. That's how you draw force diagrams. I hope that makes sense. I'm going to do one more. Elevator. So if I have an elevator and somebody's standing in an elevator, they're experiencing two forces. Again, Fg down, of course, we'll make that negative, I'll make positive up, so normal force is positive. I like writing those to remind myself that they're positive and negative. You don't have to, but I like that. I know if you don't write negative, it's implied as positive, but this, remember, means something. It means up. So I like writing positive. Positive is up, positive is up. I like writing that. Anyway, so F net on this individual will be F net minus, sorry, F normal. F net is F normal minus mg no matter what. Now, what's the acceleration? Well, let's say that I know the normal force, say that this person feels on the scale that the normal force is twice their weight. You can do numbers if you like. Let's say the mass of the person is 60 kilograms. That means mg is 588 newtons, m times g times 9.8. So that means 2 mg, if you want to do that, will be twice that, 1,000 plus 160, so 1176 newtons. I'm going to keep it in terms of pure variables, which I think is more illuminating. That no matter what, if the normal force is twice the weight, what is the acceleration? Here's how you do it. Well, you know this is true. You drew your diagram, you drew this. We don't know where acceleration points, but I know that this is true. So what I can do is set normal force minus Fg equal to ma. Notice this is step 1. This is step 2. F net from the force diagram only, no matter what, and then set it equal to ma. That's step 2, two separate things. And then we solve for whatever we need to solve for. Step 3 could be acceleration is change in velocity over time, or F normal equals something, or something else, right? In this case, it's this one, because I was given this, right? Or whatever is given. Whatever we know. So step 1, step 2, step 3. So step 3 in this case will be this one, where I'm going to plug this into here. Let me do that in a different color. This whole thing goes into there, which means 2mg minus Fg, which is mg, right? Remember, this is mg. Equals ma. The masses all cancel. 2g minus g is g equals a. And you might say, wait, what does that mean? it means the acceleration is positive 9.8 meters per second per second. So be careful. Positive means what? So you might say, wait, is it in free fall? If it's in free fall, the scale should not be heavier, right? This means the person feels heavier. And if the person feels heavier, I hope you can conclude that means the person's accelerating upward. It means the net force is upward. It means Fn is greater than mg. And it is, it's twice the weight. So if the person feels twice as heavy, they're accelerating upward. Whether they're slowing down if they're in descent and it's stopping them, or they're just accelerating upward. If you ever feel yourself in an elevator accelerating upward. Indeed, here it's upward. That the acceleration just happens to be the acceleration of gravity upward, not downward. If they were in free fall, they would feel nothing. The normal force would be 0. Right? So this is my little separate. Let me draw this in a separate bubble. Separate analysis there. So this is the answer. That A equals positive G. You're like, okay, I got that. I did the algebra. You feel good about yourself. You're like, all right, I did it. But that's not the end. What does this mean? First of all, it was positive. You can do numbers. If you did these numbers, by the way, you would have gotten the same answer. You would have gotten A is positive 9.8. That positive matters, and I would write it. So that means positive upward 9.8, which means it's accelerating upward at the same acceleration of gravity, which should make sense. That means the total normal force counters gravity and adds an extra mg upwards. So feel twice as heavy. That's it. If you want on your own, what we also did in class, you can recall, say the normal force equals 10 mg. Well, then you would do 10 mg minus mg equals ma. Mass cancels. I get A equals positive 9g upward. Notice how you can sort of, this is what you do, like in 2 steps. I would go back and know why you do that and follow all the steps and know how to do that on your own. Say normal force is half mg. Ooh, now it feels lighter. Right? This is heavier. Notice that the more the acceleration, this is called 10 Gs. They feel 10 Gs. And you're feeling 10 times the force of gravity if this is your acceleration upward. Here we go, we'd have half mg minus mg equals ma. Remember here the net force, Fn minus Fg equals ma is the setup just for this question. For an elevator question, this is what you're going to do every time. So I have, careful, I have half an apple minus 1 apple. This is implied 1. Half an apple minus 1 apple is negative half an apple equals ma. M cancels, and I have a equals negative. I'm going to rewrite it. So I say a equals negative a half g. It's negative, which means it's downward. So this would be if the elevator were accelerating downward at half of gravity, then you feel half as heavy. And that should make sense. I hope that makes sense. Right? Now be careful. If it was 3/4 gravity, you would subtract. It's just because half minus 1 is a half. So be careful. Don't say, okay, if it's 3/4 gravity, I feel 3/4 lighter. Careful. I would go through the steps. Right? Half minus 1 is a half. That's why. If it was 3/4, this would be 3/4 minus 1, which would be negative 1/4. So be careful. This is what you do. That's it. Always email me if you have any questions. Friday, study time, office hours, whatever you like, whatever you want to call it. I'll be in the physics lab. Show up. You guys are great.